Hi everyone, this is going to serve as a review before pre-calculus. So we're just going to cover a couple topics and we can jump right in here. It's going to start off with distributing. So we're just going to primarily focus on distributing polynomials. So for these questions here, distribute and combine like terms. For question 1, we're going to distribute. Remember what distribute means? Distribute means you're multiplying over addition or subtraction. So we're going to distribute this 2x cubed into every term from that second factor. So there are three different terms in this second factor in parentheses, so that 2x cubed needs to get distributed or multiplied to each one. So first, 2x cubed times x squared. We also need to remember that when we multiply common bases, we add the exponents. So x cubed times x squared is x to the fifth when you add those exponents. Now we're going to multiply 2x cubed times negative 3x. That's going to give us negative 6x to the fourth. Once again, you add the exponents. X cubed times x is x to the fourth. And then for the last one, we have 2x cubed times 5, and that gives us a plus 10x cubed. So there's no like terms to combine here. So we are done with the first one. Okay, for the next one, making it just a little bit harder, we have a binomial times a binomial. So two terms times two terms. This is when you probably remember the word foiling. To foil is just distributing a binomial times a binomial. So it's still just the same thing as what we just did, but just a little bit harder. You're going to multiply or distribute every term from the first factor into every term in the second factor. So we're going to start by distributing the x, and then afterwards we'll distribute the negative 1, but let's just start with the x first. So we do x times x, which is x squared, and then x times positive 5, so plus 5x. And now we're going to distribute the negative 1. So negative 1 times x is negative 1x or minus x. And then lastly, negative 1 times 5 gives us the minus 5. And then we just need to combine like terms. Remember, like terms are the terms that have the same variables with the same exact exponents. So like terms here are just going to be the 5x minus x, which gives us 4x. So it's going to be x squared plus 4x minus 5. And that is our final result. Okay, so for the last one here, getting a little bit harder, just taking a look at this, you can see we have a binomial times a trinomial, two-termed factor times a three-termed factor. Similar to what we just did. This is not called foiling for this one though, but very similar to what we just did. We're going to multiply every term from the first factor to every term in the second factor. So we're going to start with the x cubed, and then we'll do the negative 2x afterwards. So x cubed times 2x to the fourth. We're going to add the exponents together to combine them, and we get 2x to the seventh. And then x cubed times x to the sixth. That's going to give us plus x to the ninth when we add the exponents together. And then x cubed times negative 1 just gives us minus x cubed. And now we're going to do the same thing for negative 2x. Just make sure that negative is coming with it. So negative 2x times 2x to the fourth is going to give us negative 4x to the fifth. So we added the exponents together. Always remember too, there is an exponent of 1 when there's no exponent written, right? So we then have negative 2x times x to the sixth. That's going to be negative 2x to the seventh, 1 plus 6 for the exponents. And then lastly, negative 2x times negative 1 gives us plus 2x. And now when we combine like terms, a little bit more annoying for this one, maybe just because we have more terms than the previous ones that we just did. But it looks like we have an x to the seventh and an x to the seventh. So that means these are like terms. There's no other common exponents. So these are the only like terms. And when we combine the coefficients, 2 minus 2, that actually gives us 0. So these actually completely cancel off. So we're left with x to the 9th. Something I'm going to do here, and something I recommend doing, is when you have polynomials, so polynomials are when you have an expression where the terms exponents are positive whole numbers only in the numerator. When you have polynomials, you should write them in standard form, meaning the exponents go from largest to smallest. So I'm going to write this as x to the 9th minus 4x to the 5th minus x cubed plus 2x, and that looks like every term in order, exponents largest to smallest. So there is our final answer. Okay, so that is distributing polynomials. Multiply every term from the first factor into every term in the second factor, and then you combine like terms to simplify. All right, next concept is factoring. So in a sense here, factoring is going to be in the reverse direction of distributing. Now we're going to start with an expression, and we're going to rewrite it as things being multiplied, and those things are called factors. So there's several different techniques for factoring. These are not the only techniques, but these are the main 4 that we're going to be using. We have greatest common factor, GCF, difference of squares, quadratic trinomials, and grouping. So these are the 4 techniques that we should know going forward. And a good little hint is you should always try to do GCF first. There may not be a GCF, but you should almost always try to do a GCF first. All right, so taking a look at the first one here. So we're going to actually, every single one of these, we're going to factor these completely. So we might have to factor more than once. So taking a look at this first one, 2x to the 5th minus 8x cubed. So again, always look for a GCF first. There is a GCF here, and the GCF is going to be 2x cubed. So when you do the GCF technique, you're factoring it out front, and you're writing the GCF out here, and then you think about what is left over, and what's left over is the original expression divided by the GCF. Every term divided by 2x cubed, and when you divide common bases, you subtract the exponents to combine them. So for example, you have 2x to the 5th divided by 2x cubed. That's going to give us x squared, right? 2 divided by 2 is 1. X to the 5th divided by x cubed is x squared. Subtract the exponents. And then you have minus, so I'll just put the minus right here. You have 8x cubed divided by 2x cubed. 8 divided by 2 is 4. And then the x cubed divided by x cubed is 1. They cancel each other off. So that was GCF. This first step, I'll write it next to it, is GCF. This is going to be able to be factored one more time. This x squared minus 4, that is difference of squares factoring. So difference of squares actually tells us what the technique, what we're looking for. It is a difference, which means subtraction, of squares of things being squared. So difference of squares means we're looking for something that's in the form a squared minus b squared, something squared minus something squared. If we do have something like that, like we do right up here, then we can factor it as a plus b times a minus b. Essentially, you take the square root of a, the first one, the square root of the second one, and then you do plus, minus, and these are conjugates. A plus b and a minus b, these are called conjugates to each other. Same 2 terms, one's addition, one subtraction. So rewriting the 2x cubed right out front, when we factor using difference of squares for x squared minus 4, this is going to factor to x plus 2 times x minus 2, and then we are done. So you just had to identify your a squared and your b squared, and essentially just take the square root of each of them. The square root of x squared is x, the square root of 4 is 2, and set it up as x plus 2 times x minus 2. Okay, so that is now factored completely. And a quick double check, we have 3 different factors here. Well, you can consider maybe the 4 with the 2 and the x cubed separately, but we have, let's just say, 3 different factors to keep it simple, and none of these can be factored any further, so we are done. Okay, next one. we have for part 2 here, negative 3x to the 4th plus 6x cubed plus 24x squared. So for this one, again, try GCF first. There is a GCF. I'm going to ignore the negative for 1 second here. There's a GCF of 3x squared. And something I didn't mention in the previous one, again, I'm kind of going quickly here because this is just supposed to be a review. But when you're doing the GCF, you're going to look for the GCF for the coefficients. The GCF between 3, 6, and 24 is 3. And then when you do the GCF of the variable next, it's always going to be the variable with the smallest exponent, which is just the x squared. That's kind of like a nice quick way to do it. So you can definitely factor out 3x squared as the GCF, but a huge little hint tip here is if the leading term, the term with the largest exponent, is negative, you should also factor out a negative. That's not something that necessarily has to be done, but I definitely recommend doing it, which we'll see why in the next step here. So we're going to divide, I'll do this one a little bit more quickly. We're going to divide all 3 of these terms by negative 3x squared. So the first one divided by negative 3x squared gives us positive 1x squared. The second term divided by the GCF gives us negative 2x. And then the third term divided by the GCF gives us minus 8. X squareds cancel, so just minus 8. So that was GCF. But once again, always double check to see if you can factor again. We can factor the x squared minus 2x minus 8. This is the quadratic trinomial technique. That's what I always just call it, the quadratic trinomial technique, where if this factors, you need to think about 2 numbers. Since this is a coefficient of 1 on the x squared, if it factors to 2 numbers let me just rewrite this down so I don't make it more confusing. If it factors to x plus or minus something times x plus or minus something. And we need to think about 2 numbers that multiply to the constant term that also add to the x coefficient. So 2 numbers that multiply to negative 8 that also add to negative 2. That's going to be negative 4 and positive 2. So negative 4 times 2 is negative 8. Negative 4 plus 2 is negative 2. So that means x squared minus 2x minus 8 factors to x minus 4 times x plus 2. Again, this is that quadratic trinomial factoring technique. Okay, and then this is actually as far as it can be factored. So it is just completely done. So again, like I kind of said a second ago here, the reason why this technique will work quickly for this specific expression is because that x squared coefficient has a 1 on it. If that was not a 1, then you would have to do it a little bit differently. All right, so let's see, let's double check here. Let's see one more of these factoring techniques. So we have x cubed minus 3x squared minus 9x plus 27. So first thing you probably see here is there is no GCF between all 4 of these terms, right? So we have 4 terms here, and there's no GCF between all 4. There's a GCF between the first 3, but that's really not going to help us too much. We want a GCF between all of them. So a nice tip here is that if there's 4 terms, chances are the factoring technique is going to be grouping. So for grouping, what you're going to do is you're going to group the first 2 terms together, and then you're going to group the last 2 terms together, but there's something you have to watch out for. You have to be really careful. If the third term is being subtracted, you need to change it to plus the negative. That negative needs to be in the parentheses when you actually group them together like this. So if that third term is being subtracted, change it to plus the negative. The negative needs to be inside the parentheses. So nothing crazy yet. We just threw some parentheses around the first pair, around the last pair. And all grouping is actually GCF times 3. It's 3 different GCF in a row here. So you're going to do the GCF of each group separately. So the GCF of the first group is x squared. If you factor out an x squared, you're left with x minus 3. Then you're going to do the GCF of the second group over here. The GCF between negative 9x and 27 is negative 9. If you divide both of those terms by -9, you end up getting positive x minus 3. So in order for grouping to work, we just did GCF twice. We need to do GCF one more time. In order for grouping to work, these parentheses need to be the exact same thing, which they are. They're both x minus 3. And then the last little step here is we're going to do the GCF of the entire thing now. So basically, even though it looks like there's a lot going on, there's two main terms here. The two highlighted terms are the two terms for this overall expression. So the GCF between the two terms is going to be this x minus 3. So we're going to factor out an x minus 3 from both of these terms. And when you divide both of these terms by x minus 3, all you're left with is whatever's in front of them, which is an x squared minus 9. So that's the part that tends to trip people up the most here. So that was grouping. Everything we just did was grouping here. So we just grouped the first pair and the last pair. We did the GCF of each pair separately, and then we GCF'd the entire thing, which is always going to be that same set of parentheses. So that whole thing was grouping, but we can do this one more time because we can factor x squared minus 9 using difference of squares. Okay, so remember, for difference of squares, that's when a factor is in the form a squared minus b squared. And then if it is in that form, you can factor it by rewriting it as a product a plus b times a minus b. So I'm going to rewrite the x minus 3 out front. So x squared minus 9 is going to factor to x plus 3 times x minus 3. So this is the a plus b times a minus b, taking the square root of x squared and 9 separately. And technically we're done. That is technically factored. Something that you should do, I highly recommend doing, is notice that you have a common factor, x minus 3 times x minus 3. If you have a common factor, we can combine them with an exponent. So we can combine x minus 3 times x minus 3 as x minus 3 squared, because there's two of them, and then just rewrite the x plus 3, and then you're done. Also, so that's not something that technically always has to be done, but just trust me, it is a good idea to just make sure it's completely simplified. It is a good idea to do that going forward. Also remember, multiplication is commutative and associative, so you can write a plus b times a minus b, or you can write a minus b times a plus b, right? That all means the same thing because multiplication, the order doesn't matter. Okay, so that is it for factoring. Now let's take a look at the next couple topics, which is going to have to deal with basics of functions. So we're going to talk about evaluating functions, domain and range of when we're given a graph, and then intervals where a function is increasing, decreasing, and constant when we're given a graph. So starting off with some evaluating, let's evaluate. Let's say we're given this function, f of x equals 2x squared minus 3x plus 1. So first of all, this is function notation, right? This f of x is function notation. It is the same idea as if we have y equals. Y is the dependent variable. So instead of using y, if y is a function, we tend to use f of x, g of x, h of x. We tend to use this function notation. So just make sure you're reading it off correctly. F of x. F is a function of x. That means x is the independent variable. So we're given this function, and we want to evaluate, for the first one, f of -3. So every time you're evaluating a function, no matter what it is, you're always going to start it off the same way. You're going to start it off by substituting in this case, a -3, into all of the x's. When you do this, just make sure you substitute it in with parentheses. No matter what you're plugging in, always use parentheses. So I just replaced all of the x's with a -3 in parentheses. I can't stress that enough. And then so we probably have a calculator, but you should try to do these in your head. Order of operations, PEMDAS, you do the exponent first. -3 squared is 9. I'm just going to go ahead and do -3 times -3 is positive 9 for that second term. And then we have 18 plus 9 plus 1, 27 plus 1 gives us 28. So a nice thing to keep in mind is when we kind of think about graphs here in a little bit, this is your x value, this would be your y value, your input x and your output y. All right, next one, which looks a little bit trickier maybe, we have f of negative x. So this one looks maybe a little bit trickier just because you're now plugging in a variable instead of just a number. But again, you're going to start this off the same way. You're going to replace all of the x's in the original function with a negative x in parentheses. So that's going to be 2 times negative x squared minus 3 times negative x plus 1. So again, you always start these off the same way. You substitute in for all of the variables with parentheses. So the trick for this one, there's a nice little shortcut to remember, is if you have a negative value to an even exponent, a negative times a negative is positive. So an even exponent, they're all going to pair up. The bases are going to pair up, making it positive. So long story short, a negative raised up to an even exponent will become positive. So you can just get rid of the negative, get rid of the parentheses, and rewrite it as x to whatever the exponent is. If you have a negative to an odd power, the values are going to pair up, but there's going to be one negative left over, making the entire thing negative. So a negative to an odd power is just going to be the same exact thing, negative to the odd power, but the parentheses are gone, making the whole thing negative. So for this one that we just wrote down over here on the left, negative x squared is just going to be the same as positive x squared because it's an even exponent. The next one is technically an odd exponent, but it's probably just easy if you just look at it as negative 3 times negative x is positive 3x. Negative times a negative is positive, plus 1 at the end, and then we're done. So if you're plugging in a variable, you're actually creating, this would be something similar to a composite function. You're creating another function, essentially. Right, and then one more of these ones. Let's say we have f of x plus 2. So looking at this one probably looks the most complicated, right? Now we're plugging in an x plus 2. So we're going to go all the way back up here, and we're going to replace all of the x's with an x plus 2. So instead of 2x squared, it's 2x plus 2 squared minus 3x plus 2 plus 1. So let me go ahead and write that down. So that's going to be 2 times x plus 2 squared minus 3 times x plus 2 plus 1. So again, look at the one we just did compared to this one. Same idea. You just replace all of the x's with whatever you're substituting in with parentheses. So step 1, good, we substituted it in. Now the question is, how do we actually simplify this? So this is actually going to come down to distributing and combining like terms. So hopefully you agree this second term isn't that bad. We're just going to have to distribute the negative 3. The part that makes this a little bit annoying is this first term, the x plus 2 squared. So you have two options for this. The x plus 2 squared, you can either write this as x plus 2 times x plus 2, because that's what x plus 2 squared is. And then you would distribute, just like we did a little while ago, and combine like terms. Not the end of the world, won't take that long. There is a nice shortcut that you really should know here. It's when you have a binomial squared, a plus b, so something plus or minus something squared, a plus b squared. You can do a plus b times a plus b and FOIL it out to know what to see where this comes from. But when you expand this out, it ends up being the first one squared plus the second one squared, a squared plus b squared. But there is a third term. It's both of them multiplied together, a times b times 2. So I highly recommend knowing this shortcut when you have a binomial squared. So let's go ahead and use that shortcut. I'm going to start by writing down this 2 that's out front. Note that you cannot distribute this 2 right away because there's an exponent right here. So what we're going to do is we're going to take a look at this shortcut right here for x plus 2 squared. So this is going to be the first one squared, so that's just x squared, plus the second one squared. 2 squared is 4. And then the third term is the one that's hard, that usually people tend to forget how to do this one. It's both of these multiplied together times 2. X times 2 times another 2 gives us 4x. So basically, I just use this shortcut over here. A squared plus b squared plus 2ab. Again, the order doesn't matter. Addition is commutative and associative. I just use the shortcut. Try to remember that shortcut because you can use that a lot going forward. All right, and then for the second term, like I said a minute ago, all we have to do is distribute this -3. We get minus 3x minus 6 plus the 1. And before we combine like terms, let's just go ahead and distribute this 2. So 2x squared plus 8 plus 8x minus 3x minus 6 plus 1. Now we combine like terms. So that's 2x squared. We have x terms. 8x minus 3x is positive 5x. And then we have a couple constants. 8 minus 6 is 2. Plus 1 gives us 3. Okay, so that one a little bit messier, but that's definitely stuff that we'll see going forward. Okay, next thing is going to be domain and range, and the intervals where the function's increasing, decreasing, and constant. And we're given a graph here. So when we think about domain and range, the first thing you should think of really quickly is domain represents x values, range represents y values. So for the domain, also taking that one step further, domain is the set of x values where the function exists, and range is the set of y values where the function exists. And we're actually going to write all of these in interval notation because these are going to have to be represented with an interval. So what I like to do here is just take a look at the function first to just kind of see what's going on here. Take a look at the graph and notice that this is continuous, right? You can draw this whole thing without picking up your pencil. So for the domain, we're going to go to the leftmost point and the rightmost point. So the domain, I'm just going to use a D for domain. The domain's leftmost point, notice that there is an arrow, right? There's an arrow going to the left. We don't care if it's going up or down. We care if it's going to the left or right here because domain is x values, the horizontal movement. So since this is going to the left, that means the domain is going to be from negative infinity. There's an arrow, so it's going to keep on going forever to the left. So negative infinity. And then it also goes right to this point, which is an x value of 1, 2, 3, 4, 5. It looks like that's an x value of 6. So the domain here, the leftmost x point to the rightmost x point, is negative infinity to 6. Separate them with a comma for interval notation. And for the kind of how you use parentheses and brackets for interval notation, the infinities, negative and positive infinity, always gets a parenthesis. Since you have an open circle, that also gets a parenthesis. If that was a filled in circle, then you would put a bracket. So this parenthesis means you do not include it. Bracket means you do include it. So the domain is negative infinity to 6. That just means the function exists from x coming from negative infinity to x equals 6, but not including 6. So for the range is y values, right? So R for range here. Range is going to be the smallest y value to the largest y value. Where does the function exist all the way to the bottom y value? So again, when you're looking at the bottom y values, like how low does that function get? You might look at these 2 points right here. So the point on the right stops right there. The point on the left has an arrow going down. So the arrow going down is going to go down further. Since the arrow is going down, that's coming from negative infinity, right? So arrow going down from the y values from negative infinity. And now we ask ourselves, what's the highest point on the graph? The highest point on the graph is this point right here. There's no arrow going up, so this is the highest point on the graph. This is a y value of 1, 2, 3, 4, 5, 6, 7, 8. This is a y value of 8. So that is the highest y value that the function gets to. So something else to keep in mind here, This is the curve itself. The curve itself counts as a filled in circle. So a filled in circle would get a bracket because we include 8. It actually gets to a y value of 8. All right, so that is domain and range. Domain x values, leftmost x to rightmost x. Range y values, bottommost y to topmost y. Now let's take a look at these other questions here. We want to know where is the function increasing, decreasing, and constant. So something to keep in mind for these types of questions, increasing, decreasing, constant, we're still going to do these in interval notation. What you need to do is scan left to right. If it's rising left to right, it's increasing. If it's falling left to right, it's decreasing. Horizontal lines are where the function is constant. Something else you need to keep in mind is you're only talking about that you're only writing domain for these, so x values only, and only using parentheses. Even though it's interval notation, you're never using a bracket for these endpoints for increasing, decreasing, constant, because it can't really be increasing at the endpoint of a curve. So what I like to do first is let's label them before we actually write down the intervals. So when we skim this left to right, it's going to be, I'll highlight it, it's rising left to right until it gets to that little relative maximum point. So this is actually increasing. This is what makes it confusing for some people because they see this arrow going down and they say, oh, it's decreasing here. The function is not decreasing. You need to always skim it left to right. Since we are going up left to right here, this is increasing over the interval. Because increasing, decreasing, constant is literally at like those words are literally saying what are the y values doing as x gets larger. So that first interval is actually increasing. And then once we get to that little point up top, the top of the hill, it starts to fall left to right. So that would be decreasing. And then once we get to this horizontal line, these are probably the easiest ones. This is a constant one because constant interval, horizontal line. And then it is falling again, so that is decreasing once more. And then lastly, it rises left to right, so that is increasing. So we have several different intervals here, at least one for increasing, decreasing, and constant. So let's take a look at the increasing intervals first. So increasing intervals are these two highlighted intervals over here on the right. So when we write this, we just need to remember x values only. So x values from here to here, right, for this first interval. So that's going to be increasing from negative infinity because the arrow is going to the left. And then it's going to be increasing from negative infinity to this point here, which is an x value of negative 3. So it's increasing over the interval negative infinity to negative 3, only x values interval notation, only parentheses for these intervals. And then we also said it's increasing over this interval over here. That's going to be from this point down here to this point up here. So it's going to be from this x value, which is 1, 2, 3, 4, 5, from an x value of 5 to an x value of, it looks like 6 for this one. So it's increasing again from x equals 5 to x equals 6, parentheses only. And when you have more than one interval, you can just write it just exactly how I just wrote it here. You can write it with a comma. Technically, the way you're supposed to do it is use the union notation. It looks like the little U shape. That just kind of is saying it's joining the intervals together. It's saying negative infinity to negative 3, and then also 5 to 6. All right, let's take a look at decreasing. It is decreasing over these two intervals. Let's do the one on the left first. So it's decreasing from this point to this point, x values only. This is negative 3 to negative 1, right? So it's decreasing from negative 3 to negative 1, negative 3 comma negative 1, parentheses only. Something else to keep in mind, interval notation, the smallest number is first every single time. So negative 3 comma negative 1. And then we said it's also decreasing on this second interval over here on the right. this highlighted region over here on the right, which is an x value of 3 to 5. So x value of 3 to 5, parentheses only, put the union symbol just to represent that we have another interval. And then lastly, where is this constant? We only had one interval right here where it's constant. That's an x value from -1 to +3, right? So -1 to +3, only writing the x values, parentheses, and then we are done. So just even though we did interval notation for every single one of these questions, domain, range, increasing, decreasing, constant, kind of have them separated in your head just so you remember the last three, increasing, decreasing, constant, that we just did. X values only, parentheses only, scan it left to right, and then domain and range. Domain is x values, range is y values. Domain should be your obviously left to right because it's x values, but then range is bottom to top because it's y values. So even though these look like ordered pairs, x, y, these are not ordered pairs. This is interval notation. Right. Let's take a look at the next concepts here. So these are going to be some what I just like to call linear concepts and linear functions. Couple formulas. We have the slope formula. We have the point slope form for the equation of a line, slope intercept form for the equation of a line, and then graphing linear functions. So I'll just write them all right here. The slope between 2 points, we know slope measures steepness, like how steep would the line be connecting 2 points. It's the difference in the y coordinates divided by difference in the x coordinates. And we usually denote slope with an m. So y2 minus y1 over x2 minus x1. For the point slope form for the equation of a line, this would be y minus y1 equals m times x minus x1. This is actually the same thing as the slope formula. They're all derived from the same slope formula here. So the point slope form, this is an equation of a line, which means x and y stays as x and y. It stays as the variable. And x1, y1 represents a point that the line crosses through. M represents the slope. Slope intercept form, this is another equation of a line. It's if you essentially solved the one above for y, you would get y equals mx plus b. B is the y-intercept, m is the slope. And then usually slope-intercept form is going to be the best format when we're graphing linear functions. All right, so let's take a look at the first one here. Determine the slope of the line passing through these points. So right away, slope, we say slope m is y2 minus y1 over x2 minus x1. And you can just label the first point x1, y1, the second point x2, y2. You could flip that. You can label the first one x2, y2 if you really wanted to, and you're going to end up getting the same answer. So when you plug these in here, the difference in the y coordinates, 5 minus 3, y2 minus y1 over x2 minus x1. So once again, that's from right over here, -4 minus -2. Just be careful when you're doing this. 5 minus 3 is obviously 2, but the denominator, that's -4 plus 2, which is -2, right? So just be careful when you're subtracting the negatives. Always simplify fractions. This actually simplifies to a nice integer. This simplifies to -1. So the slope here is -1. Also, between these 2 points, also remember a positive slope means the line is increasing. A negative slope means the line is decreasing. All right. Next one, we want to determine the equation of the line in point slope form and slope intercept form for a line that has a slope of -2 and it's passing through the point 3, -6. So first, what I'm going to do here is, as usual, start off with whatever formula or equation you're using. Point slope form is y minus y1 equals m times x minus x1. And yes, I do think you should have all of these little formats and equations for the lines memorized. So we write this down, and we are straight up given that the slope is -2, and a point, it could be any point, and we'd end up getting the same result here, but we're given this point. The point that it passes through is 3 negative 6, that is your x1, y1. So all we have to do is plug these three things right in here. That's going to be y minus negative 6 equals negative 2 times x minus 3. Again, you're only plugging in x1, y1, and m. X and y stay as x and y. They stay as the variables because we're creating the equation of a line. So something you should do here is right away, when you see minus and negative, change it to plus the positive, right? Y minus negative 6 is y plus 6. So this right here, this is point slope. I'm just going to write PS again. This is the point slope form for the equation of this line. So I'll circle this one. This is point slope form, but we also want slope intercept form. So if you want slope intercept form as well, y equals mx plus b, all you have to do here is distribute the slope. So we get y plus 6 equals negative 2x plus 6. Distribute the negative 2. And then to solve for y, we just need to subtract this 6 to the other side and combine like terms. And we actually get the 6's cancel off here, which obviously does not always happen, right? The 6 minus 6 gives us 0. So this would represent our slope intercept form, SI for slope intercept form, y equals mx plus b. So these formats, these equations are the same exact line, they're the same exact thing, but the one on the bottom is solved for y, which makes it in slope intercept form, whereas this one up top is in point slope form, but they represent the same, they are the same exact line. Right, so let's get into some graphing. So we're just going to focus on graphing these lines that are in slope intercept form. So most of these are in y equals mx plus b, slope intercept form, right? So what makes this a line is that the exponent is a 1. If the exponent is not a 1, if it's literally anything else other than 1, it is not a line. I guess technically if it's 0, like we're going to see down here, it's still a line, but we'll get to that in a minute. But if that exponent is a fraction, if it's 2, 3, whatever, then it's no longer a line. So when you're graphing these, you could create an XY table if you want. You can plug in any X values you want and get out the Y values, plot the ordered pairs, connect them as a line. But the easier way to do it is identify the y-intercept, which is the constant, which is 2, and then identify the slope, which is whatever is multiplying the x, which is negative 3, and then use those two values to create 2 points, connect them as a line, and you're done. So you're always going to start by just plotting the y-intercept. So the y-intercept is 2, so you just plot the y-intercept, 2, piece of cake on the y-axis. The part that's a little bit trickier, that could be a little bit trickier, is the slope, negative 3. You always want to write this as a fraction. Negative 3 is the same as negative 3 over 1. So this is going to be your rise over run. And the way that I like to do it, that I always explain it, is you're either going to go up and to the right or down and to the right. So this is not a second point. From this y-intercept, you're going to go down 3 because it's negative, and to the right 1. So a positive slope, you're going to go up and to the right, up the numerator, down the denominator. Up the numerator, right denominator. If it's a negative slope, you're going to go down numerator, right denominator. So from this point, we're going to go down 3, 1, 2, 3, to the right 1, and we're going to put another point. And then all you got to do is connect them with a line. Obviously, it's not going to be perfect. Connect them with a line. You could make more points if you want to using that slope. You don't have to. Leave it just like that, and you're done. Maybe label it with the function notation, f of x, and that's good. So y-intercept is your first point. Use the slope to find the second point. Positive, go up to the right. Negative, down to the right, and that's it. For a line, lines are great to graph because you only need 2 points to graph them accurately. Next one, we have y equals 4/5 of x. So this time there's no plus or minus number. So that means the y-intercept is 0 because it's plus 0. The slope here is 4 over 5. So we're going to start by plotting the y-intercept, which is 0, which means it's right at the origin. And since this is a positive slope, we're going to go up and to the right. Basically, as long as you do it the same way I do it, you can always just go to the right for the denominator, as long as you're going up when it's positive or down when it's negative. So from this point, we're going to go up 4 and to the right 5. And we're going to put another point, connect them, and you're done. So up 4 to the right 5, there's our linear function, and we are done. Label it if you want to. Okay, let's see one that looks a little bit different. We have y equals 7. So for this one, you probably notice there's no variable, right? This is just y equals a number. If it's y equals a number, this is always just a horizontal line. There's no x here. Y equals a number is a horizontal line. So you're going to go to 7. 1, 2, 3, 4, 5, 6, 7. You're going to go to 7 on the y-axis. And you're going to put a horizontal line. And you're done. So basically, another way I like to think of this is two more ways to think of it. You could say this is y equals 0x plus 7. A slope of 0 would just be flat, right? You're going up 0 to the right 1, technically. And the y-intercept of 7, that's one way to kind of rewrite this. Or you can think of this as y is always 7. No matter what x is, y will always be 7. All right, so that one's a piece of cake as long as you remember that little rule. Let's see the other one. So now we have x equals a number. So this one looks a lot different, right? This is not anywhere close to the form y equals mx plus b. This is x equals a number. Anytime you have x equals a number, this is a vertical line. So you're just going to go to negative 6. 1, 2, 3, 4, 5, 6. Negative 6 on the x-axis because x equals negative 6. And you're going to put a vertical line with, notice, make sure you have arrows on the end of these also. Put a vertical line, and then you're done. So y equals a number is horizontal at the y-intercept. X equals a number is vertical at the x-intercept. So those ones are the quickest ones to do, as long as you remember, how to do them, obviously. Right, next one, we have a couple more topics here, linear equations. So I'm just going to do one kind of big linear equation here. So when you're solving linear equations, first of all, it's an equation, right? So there's an equal sign. So we're going to be solving these for x. We're looking for the x value that makes these true. What makes this linear is that the exponents are all 1. So these exponents are all 1. That's what makes this linear. And then it's an equation because there's an equal sign. So when you're solving linear equations, technically there could be no solutions, infinitely many solutions, or one solution. Usually there's one solution. Keep in mind it could be the other possibilities also. So the great thing about linear equations is you almost do these the same way every single time. You're going to work with both sides of the equal sign separately, and we're going to distribute and combine like terms first. So let's go ahead and distribute. So basically I'm looking for all these parentheses, seeing if there's a number out front, and we're going to multiply that number in. We're going to distribute all of those numbers. So for the left side, we have 7x minus 2x minus 1, right? We distribute that. Technically, it's a negative 1 that we distributed. And then on the right side, we're going to distribute the 4, so 4x minus 8, and then distribute the negative 6, negative 6x minus 6. Think of that as your step 1. Everything is distributed. Now we're going to combine like terms on both sides of the equal sign separately. 7x minus 2x is 5x. And then on the right side, we have 4x minus 6x gives us negative 2x. And then we have some constants. We have 5 minus 8 minus 6. 5 minus 8 is negative 3. Minus 6 is negative 9. Be careful with the negatives, obviously. So now everything is, all like terms on both sides are combined. Now for the last little steps here, we're going to get all variable terms on one side of the equation, constants on the other side. I like to move my variables to the left usually, which means we need to move negative 2x to the left. You always do the inverse or opposite operation. Since this is a negative 2x, we're going to add 2x. Just make sure you're combining like terms. So add 2x to both sides. That gives us a 7x on the left. 5x plus 2x is 7x. In one step, let's move the constants to the right. So I'm going to move, I want that negative 1 on the other side, on the right side. And again, this is subtraction, so we're going to add it to both sides or add it to the right side. Opposite operation. Negative 9 plus 1 gives us negative 8. And now we can go ahead and finish solving right here. I'm just going to condense this so they're a little bit closer. 7x equals negative 8. So to finish solving this for x, we need to get rid of this 7, right? We need to move that 7 to the other side. This is multiplication, 7 times x. The inverse of multiplication is division. And when I'm saying inverse, you can kind of think of it as opposite. That's kind of a bad word in math, though. You're thinking of how to cancel it to move it to the other side. So we divided both sides by 7. We get a fraction, which is completely fine. We get negative 8 over 7, and we're going to leave it just like that. Remember, you could check your answers for equations. You could go back up and plug negative 8 over 7 into every single x and simplify both sides of the equation separately, and you should get the same exact thing as long as you did it correctly. I'm not going to do it just for time's sake, and fractions kind of messy here. Right, so those are linear equations. Let's move on to the next thing. And next thing is quadratic equations. So we just did linear equations. The exponents on the variable was just a 1. Quadratic equations, like you can see in this first example, now you're going to have, you might have an exponent of 1, but the highest exponent will be 2. That's what makes it a quadratic equation. Unfortunately, these are a little bit harder. There's a couple different ways you might be able to solve these. So the first way that I have here is the quadratic formula. It's this formula that comes from completing the square on like your basic quadratic equation. So for example, if you're solving ax squared plus bx plus c equals 0, that's a quadratic equation. A, b, and c represent numbers. Then the answers, the x values, the answers to this is the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you want to like look up, I'm not going to go over right now just for time's sake, where this comes from, it's completing the square on ax squared plus bx plus c equals 0. You should have that memorized. So the quadratic formula always works, but it may not be the quickest way to do these. Sometimes you're going to be able to use factoring that we talked about a little while ago, or the square root property, which is essentially just solving for the squared term and square rooting both sides. We'll get to that in a little bit. And then completing the square. I'm not going to do one of these just again for time's sake, but completing the square is a technique that does also work. So let's just solve these and see like what techniques we should use. So also solving these equations, the reason I'm going over these right now is 1, we should know how to do these, and 2 is this is going to help us find x-intercepts for functions going forward. All right, so for this first one, x squared plus 8x plus 12 equals 0. So we can first recognize all 3 terms are on the same side, 0 is on the other side. If you have all 3 terms on one side, 0 on the other side, you could skip to quadratic formula if you really want to, but notice that this one factors, right? So think back to what we just did a little while ago. 2 numbers that multiply to 12 that add to 8, that's going to be x plus 6 times x plus 2, right? 6 times 2 is 12, 6 plus 2 is 8. So this does factor. And again, we were able to do this technique because it was a 1 coefficient on the x squared term. So once you have it factored, what you're going to do next, I'm going to show my work just really quickly, is you're going to do what's called the zero product property. If you have something times something times something times something times something, if you have something factored, multiplication only, and it's equal to 0, it has to be 0, The only way you multiply things to get 0 is if one of those things is 0, right? So anytime you have something times something equals 0, you can finish solving by setting them both equal to 0 separately. And these are really small linear equations. Subtract 6 on both sides for the one on the left. We get x equals -6. Subtract 2 on both sides for the one on the right. We get x equals -2. So we get x equals -6 and -2. We get 2 answers for this one. So if you have to show your work like that, that's fine. Once you get to this point right here, try to do it in your head. Try to say to yourself, x plus 6 equals 0. Subtract 6, that's just going to give you -6. X plus 2 equals 0. Subtract 2 on both sides, we get -2. So quadratic equations, you can have at most 2 answers. That has to do, you probably kind of might recognize this, that has to do with the exponent being 2. The largest exponent is at most how many answers you can have. All right, next one, x squared minus 7 equals 0. So again, you could use the quadratic formula. Quadratic formula is going to work every single time. So using the quadratic formula here, there's no x term, so the b would actually be 0. But something to always keep in mind when you're trying to solve any equation, if only one term has a variable, solve for that term first. So let's solve for x squared by adding 7 to both sides. And then once you have the one term with the variable solved for, you can finish solving for x by doing the inverse operation. In this case, the inverse of squaring something is square rooting something, right? So what you would do, I'm going to erase this because I don't like writing it like this, but when you square root both sides, it cancels the squared, and all you're left with is x on the left. So I don't like, if you like writing that step, go for it. Square root both sides, you get the square root of 7. Something to keep in mind though, is when you have an equation and you square root both sides, you always get a positive and a negative result. So we actually get 2 answers, negative radical 7 and positive radical 7. And you can leave it just like that. You can write them separately, negative radical 7 and positive radical 7 if you want to. Doesn't matter. Represents the same exact thing. So this one right here, like I mentioned at the top of this page, this is called the square root property. When you can solve for the squared term and just square root both sides, notice there is no x term, right? It's just something squared, no x term. So that's when you can use the square root property. Right, next one. We have x squared minus 3x minus 1 equals 0. So you might try to factor this and you think, what are 2 numbers that multiply to -1 that add to -3? You're not going to get 2 integer values, 2 positive or negative whole numbers that are going to do this. So we would say that this actually does not factor. So if it doesn't factor, you can and should go right to the quadratic formula. So the quadratic formula, for whatever reason, people tend to not like it. You just have to be careful. Make sure you have it memorized. Be careful when you plug stuff in. A is 1. B is -3. C is -1. Remember, these are just the coefficients right in order, 1, -3, and 1. And when you plug stuff in, just like we did a few pages ago, anytime you plug anything in, whether it's a function, a formula, whatever, maybe except for the slope formula, you should use parentheses. So for -b, that's -3. So be careful with the negatives, plus or minus the square root of b squared, -3 squared minus 4 times 1 times -1, all over 2 times 1. So I just plugged in a, b, and c into all of their spots. Parentheses around everything I plugged in. Again, make sure you do that. If you don't do that, I almost guarantee you're going to get something wrong, because you actually need parentheses in this case around the b squared, or else it will give you the wrong answer. All right, so when we simplify this, don't panic. It's not as bad as it looks. For the first part, -3 is just +3. And for the denominator, 2 times 1 is just 2. So this is the part that gets messed up the most, but I recommend doing it in two steps here. First, b squared negative 3 squared is positive 9. B squared is always a positive number when you square something, unless it's 0. It's always going to be positive. A negative squared is positive. So that's the first mistake people make. So positive 9. And then for this next part, what I like to do is just count the negatives. We have two negatives here, right? We have this negative and this negative. A negative times a negative is positive. If you have an even number of negatives, it's going to be plus. If you have an odd number of negatives, it will be minus. So once we know it's plus, all we got to do is 4 times 1 times 1, which gives us 4. So once you do it, if you do it that way, then the next part is pretty much done here, because all you have to do is 9 plus the 4 gives us 13, and then you're actually done. So this 13, this radical 13, that's 13 is not a perfect square, right? So you can actually just leave it like this. You can plug it in the calculator if you really, really want to, and it'll give you a decimal for both of these. But usually you can just leave it like this, and that's fine. So we get two answers: 3 minus radical 13 over 2, and 3 plus radical 13 over 2. But again, you can just leave it as plus or minus. Completely fine. Right, let's do one more of these, and then we just have one more quick concept to talk about. So 2 times x minus 1 squared minus 8 equals 0. So this one looks pretty different than the ones we just did, right? The ones we just did, like x squared minus 3x minus 1, x squared minus 7, x squared plus 8x plus 12, these had everything equal to 0, just like this one, but it didn't have, none of the ones we did had this little binomial squared term. So this one looks a little different because we can't use the quadratic formula right away. You could distribute and combine like terms and then use the quadratic formula, maybe factor also. But anytime you have this binomial squared term, there's a nice way to do it, and that's just going to be using the square root property. We can solve for the squared term, which means all we have to do here is start by adding 8 to the other side to cancel it on the left. And before you take the square root of both sides, we still have to get rid of this 2, and we have to do that with division because it's being multiplied. Divide both sides by 2. We get x minus 1 squared equals 8 divided by 2 is 4. So I like to think about that as your step 1. And then just like we did a few examples ago, we just solved for the term that is squared, even though it's a little bit different looking. All we have to do is take the square root of both sides now. So I'm going to erase this in a minute because I don't like it, but just so I can show what I'm doing. Square root both sides, and it'll cancel the squared. And then we're left with the square root of 4 on the right. But again, you always get plus or minus the square root when you square root both sides. And we can actually simplify this further. Radical 4, the square root of 4, is 2. So we're left with x minus 1 equals plus or minus 2. We still have to finish solving this for x, which means we have to add 1 to both sides. So usually this looks pretty weird, right? Plus or minus 2 plus 1. You can write these separately. Usually it's good to write the plus or minus number second. Technically it doesn't matter though. So I'm going to write this as 1 plus or minus 2. If you want to, write it as plus or minus 2 plus 1. And now we can actually do these separately. So now we can split this up and say that's 1 minus 2 and 1 plus 2, which gives us negative 1 and positive 3. So we get two answers. I'm going to write it like this: x equals negative 1 and positive 3. So this one kind of looks messy, but if you have just a binomial, like there's only one variable here, just the x minus 1 squared, one term with the variable, you're going to solve for it, and then you're going to square root both sides, and then finish solving for x just by using addition or subtraction. Right, so those are some quadratic equations. So there's one more thing here, and this last thing can be a little bit tricky, but it's going to come in handy when we talk about some inverse functions going forward. So inverse functions. So a couple little tricky concepts. First of all, a function will only have an inverse function if they pass the horizontal line test. So if we're able to either have the graph or figure out what the graph of a function looks like, we can determine if it has an inverse function if it passes the horizontal line test. So it's pretty similar to the vertical line test. The vertical line test tells us if a graph represents a function. The horizontal line test, pretty similar idea. As long as any horizontal line only intersects the curve once, the function has an inverse function. If it intersects more than once, it does not have an inverse function. Whatever passes the horizontal line test, these are called one-to-one functions. So the notation, we have this notation for inverse functions. This right here, f inverse, that's a -1, right? You don't think of that as a number, even though it's very clearly a number. You don't think of that as a number. You read that as f inverse of x, an inverse function for f of x. So the notation is kind of annoying in my opinion because it looks like it's f to the -1, because that's literally what it says, but that's not what it is. So f inverse of x. So the definition of an inverse function here is if you take an inverse function as the input to the function, they're going to cancel each other off, and you're just left with x. Same idea the other way. If you take the function as the input to its inverse, they cancel each other off, and you're just left with x. These are essentially taking composite functions when you input one function into the other function. So you kind of already know this, because if you end up looking at like x squared, y equals x squared, and y equals the square root of x, if you take composite functions of these, so if you plug in x squared into this x right here and do the square root, they cancel each other off and you're just left with x, right? So we know that the square root of x and x squared are inverse functions because they cancel each other off. So a couple really important properties of inverse functions is the domain and range are completely flip-flopped. The domain of a function is the range of its inverse, and the range of a function is the domain of its inverse. So basically, the x, y ordered pairs are completely flip-flopped. The domain of a function is the range of its inverse. The range of a function is the domain of its inverse. So what that means graphically is that inverse functions are reflections of each other over the diagonal line y equals x. And then lastly, you can find inverse functions. Like if you're given a function and you want to find its inverse function, you can find the inverse functions. The shortest way to kind of think of it is interchange the x's and y's. All of the x's become a y, and all of the y's become an x. And then you solve for y. That's how you find an inverse function. So let's just start off with these first questions using the horizontal line test. So do these graphs have inverse functions? Both of these graphs are functions, right? Both of these graphs will pass the vertical line test. So both of these are functions. But notice that if you put a horizontal line, let's say right here, it's going to intersect more than once. So this first graph does not have an inverse function. It will still have an inverse, but the inverse will not be a function. For the second one on the right, no matter where you put a horizontal line, I'll put it up here, doesn't matter where you put it, skim a horizontal line from bottom to top. No matter where you put that horizontal line, it only intersects once, which means it passes the horizontal line test, which means it does have an inverse function. Right, next one, we want to figure out, are these inverse functions? So basically what we're doing here is we're trying to figure out, two things. We're trying to figure out that if we plug G into F, and if we plug F into G, will they cancel each other off to just X? So basically we're saying, does F of G of X equal X? Question mark. And does G of F of X equal X? Question mark. And again, this is composite functions when you're taking one function as the input to another. I didn't review it on here because I'm kind of reviewing it right now. So let's take a look at this one first. F of g of x. So we're going to start with f, right? Here's f of x. You're going to start with f 2x plus 1. So 2x plus 1. But instead of an x, you're plugging in g of x. So basically, f of g of x, what this means is you're replacing the x's with x minus 1 over 2. So x minus 1 over 2, you're replacing all of the x's with the other function, and then you're going to simplify this. So when you simplify this, notice you can do 2 divided by 2, cancels the 1. You're left with x minus 1 plus 1, and then the minus 1 plus 1 gives us 0. That gives us just x, right? I'll put equals here. So this is actually good so far. F of g of x equals x. Perfect. That's what we were trying to figure out to see if they are inverse functions. Let's do the other way. G of f. So now we're starting with g, and we're going to plug in f into all of the x's in g. So just kind of notice we're doing the exact opposite thing. We're starting with g, and we're going to substitute in f into all of the x's in g. So instead of x minus 1 over 2, it's going to be blank minus 1 over 2. We're going to go ahead and plop in the 2x minus 1. So x minus 1 over 2 becomes f of x minus 1 over 2. And then we're going to simplify this. So for the numerator, notice that the that should be a plus 1, right? It should be a plus 1. Notice that in the numerator, the 1 minus 1 cancels, and we're just left with 2x over 2. Then the 2's cancel, and we're just left with x, which is what we wanted. So since when we plugged one function into the other one, and they both simplified to just x, yes, these are inverse functions. So if you got anything other than x, if you got 2x, if you got 3x, if you got x minus 7, if you got literally anything other than x, then they would not be inverse functions. That goes for either one of these or both. Anything other than x, not inverse functions. Inverse functions need to completely cancel each other off, so you're just left with, in this case, the independent variable x. Right, so that is actually it for the review.